Hi everybody, so this week we're going to be working on chapter 13, which refers to differential calculus part 2. So the learning objectives for this chapter are the following. First of all, finding the derivative of a composite function, finding the derivative of a function in the form of a product or quotient. Remember that product is multiplication and quotient refers to division. Finding the derivative of trigonometric and inverse trigonometric functions, finding the derivative of exponential and logarithmic functions, finding the rate of change of a variable that is defined implicitly, or what's called implicit differentiation, finding the rate of change of a variable from the relationship between two or more rates of change. That's what is known as related rates. Solving problems requiring a solution that is optimum, that is, a maximum or a minimum. That's called optimization. And finally, using L'Hopital's rule to evaluate a limit that is in indeterminate form. Okay, so we start with section 13.1, derivatives of composite functions, products, and quotients. So, when do we apply the so-called chain rule? Now, if you look at this table that I have here, on the left-hand side, you can see different cases where we can differentiate directly. So, for example, we know that the derivative of cosine is negative sine. We know that this next function is simply a polynomial where we use the power rule. Same thing here, because this is equal to 1/3 x to the minus 2, so we would just use the power rule for this one. And then the derivative of sine of x is cosine of x. On the right-hand side, we see other cases where there is a composition of functions. So this is not just cosine of x, this is cosine of 3x. So that means that we have two different functions. Just like in this other case, we have a square root and then a polynomial contained in the square root. In the next case, we have a reciprocal, but the denominator has a function. Very well, so this is how the chain rule works. So notice that here they have the derivative of a composite function, because this is f of g of x. So if we want to do the derivative of this, we would have to do the derivative of the outside function with the inside function unchanged. So this is one of the key things here, because a lot of people forget this, that you have to leave the inside unchanged when you do the derivative of the outside. And then you multiply it times the derivative of the inside functions. So here they have it in words. The derivative of a composite function equals the derivative of the outside function with the inside function unchanged times the derivative of the inside function. Very well, so here we are on example 13.1, and it says the polynomial function y equals 16x to the 4 minus 8x squared plus 1 is equal to this other expression, and that is the composite of u, or y equals u squared, and u equals 4x squared minus 1. Use the chain rule to find the derivative of y with respect to x. Okay, so notice that we could do this directly, right? Because if y is equal to 16x to the 4 minus 8x squared plus 1, by using the power rule, we know that the derivative of y will equal 64x cubed minus 16x. But we're not going to do it this way. We're going to use the chain rule. So notice that if we write this polynomial as a perfect square, in this case 4x squared minus 1 squared, then we're going to use the chain rule to show you that we can get the same result as before. So it says the derivative of a composite function will be the derivative of the outside first without changing or affecting the inside function, right? So this would be just using the power rule. We would go, well, this is the derivative of this here, the outside, would be equal to 2 times 4x squared minus 1 to the power 1, because 2 minus 1 is 1, times the derivative of the inside function. So that would be 8x. Now let's multiply this, and we're going to get 16x, and we have to multiply that by 4x squared minus 1, and notice that this will also give us 64x cubed minus 16x. Very well, so here we are on example 13.2, and it says differentiate each function by applying the chain rule. So I'm going to do the first three, A, B, C, and I'll leave the others for you guys to do as an exercise. All right, so let's start with A. Y equals cosine of 3x. I'm going to put this in parentheses just to emphasize the fact that we have a composition of functions. So what would be the derivative of this? So again, the derivative of the outside, cosine of 3x. Remember that the derivative of cosine is negative sine, so this would be minus sine of 3x, minus sine of 3x, times the derivative of the inside. The derivative of 3x is 3. So this times 3, and we have to rewrite it as minus 3 sine of 3x. Okay, so let's look at B, and I'm going to rewrite that as an expression with an exponent, because remember that square root is the same as having an exponent of 1/2. So we could rewrite that as 3x squared plus 5x to the power of 1/2. So then, what would be the derivative? Well, again, derivative of the outside only without affecting the inside. So that's going to be 1/2 times 3x squared plus 5x to the power of negative 1/2, because 1/2 minus 1 is negative 1/2, times the derivative of the inside, which is going to be 6x plus 5. And then we can rearrange this and rewrite it as 6x plus 5 over 2 times the square root of 3x squared plus 5x. And then finally, I'll do C. So again, for C, let's put this in a power form. And because it's 1 over that, we can just rewrite it as 3x squared plus x to the minus 1. And then what would be the derivative of that? Well, it's going to be minus 1 times 3x squared plus x to the power of negative 2, and that times the derivative of the inside, which is going to be 6x plus 1. And then we can rewrite this as negative 6x plus 1 over 3x squared plus x squared. And you don't want to expand that. Later on, you will see why. Okay, so the next example is 13.3, where they say find the derivative of the function y equals 2x plus 3 cubed, A, by expanding the binomial and differentiating term by term, and B, by the chain rule. Okay, so let's do part A first. So first of all, they ask us to expand this expression. So it's 2x plus 3 cubed. So from the rules for binomial expansion, you have to remember that this is going to equal 2x cubed plus 3 times 2x squared times 3 plus 3 times 2x times 3 squared plus 3 cubed. Okay, so then this is going to equal 8x cubed plus 36x squared plus 54x plus 27. And then now we can do the derivative of this by differentiating term by term. So the derivative of this would equal 24x squared plus 72x plus 54. So we should get the same answer in part B, but we're going to be using the chain rule. Okay, so let's just start directly with the chain rule. So if we apply the chain rule, it's going to equal 3 times 2x plus 3 squared times the derivative of the inside, and that's just going to be 2. So really, it's just going to be 6 times 2x plus 3 squared, or, which is the same thing, 6 times 4x squared plus 12x plus 9. And then if we multiply all of this by 6, we're going to get 24x squared plus 72x plus 54, which is exactly the same result. Okay, folks, so next we're going to be talking about the product rule. So let's, for example, differentiate a function that looks like this. F of x equals x squared plus 3x in parentheses times 2x minus 1. So we know that we could expand this, as you see here. You can just expand it and then differentiate the terms one by one. But is there another way to do this? Yes, there is, and that is by using something called the product rule. So this is the product rule, and it says that if you want to find the derivative of a function that is actually the product of two functions, like here we have f of x times g of x, and we'll call them factors, then the derivative of this is equal to the first factor times the derivative of the second factor plus the second factor times the derivative of the first factor. Very well, so now we are in example 13.4, where they ask us to find the derivative of this function, A, by expanding the binomial and differentiating term by term, and B, by using the product rule. Okay, so similarly, they want us to compare the two methods. All right, so for A, if we expand the expression, if we multiply the terms, we're going to get that x squared plus 3x times 2x minus 1 is going to equal 2x cubed plus 5x squared minus 3x. And then if we do the derivative of this, it's going to be 6x squared plus 10x minus 3. So by applying the product rule in part B, we should get the same answer. Now remember that the product rule says that if you have a function that is the same as having f of x times g of x, then the derivative of that is going to equal the first factor times the derivative of the second factor plus the second factor times the derivative of the first factor. So obviously we're going to call this the first factor, and this will be the second factor. So let's just substitute that into the formula. So it's going to be x squared plus 3x times the derivative of 2x minus 1, or the derivative of g of x, and that's just going to be 2. So this times 2 plus the second factor, 2x minus 1, times the derivative of the first one, which is 2x plus 3. So all we have to do is multiply and simplify this, and we should get the same result. So let's see what we get. Here we get 2x squared plus 6x plus 4x squared plus 6x minus 2x minus 3. Okay, so now we add similar terms. So this plus this is going to be 6x squared. This plus this minus this is going to be 10x. And we're left with minus 3. Therefore, we can see that we get the same answer. Okay, now, so here we are on example 13.6, where they ask us to find an equation of the tangent to the curve y equals sine of x times cosine of 2x at the point where x equals pi over 6. So this is just like finding the equations before, but with a little bit more of difficulty. Before we do anything else, I want to find the y-coordinate of the point of tangency, because I'm going to need the point of tangency later on to find the equation, and I want to avoid confusion. So, what is the y-coordinate when x equals pi over 6? Well, the y-coordinate would be equal to sine of pi over 6 times cosine of 2 times pi over 6. But notice that this is the same as pi thirds. So sine of pi over 6, that's sine of 30, that's 1/2, times cosine of 60, that's also 1/2. So this is 1/4. Therefore, the coordinate of the point of tangency that they want us to use is going to be pi 6, 1/4. So I need to keep this up here. Very well. Now I need to find the slope of the tangent. And remember that the slope is always going to be given by the derivative. So I need to find the derivative. All right, so let's start with that. Notice that we have to apply a couple rules here. We have to apply the product rule, but also the chain rule. So let's take a look. This is going to then equal sine of x. We don't alter the first factor, times the derivative of the second factor. Now notice that this is going to be minus sine of 2x times 2 plus the second factor, so that's going to be cosine of 2x times the derivative of the first factor, so the derivative of sine of x, which is cosine of x. Okay, let's simplify this and rewrite it as minus 2 sine of x times sine of 2x plus cosine of x times cosine of 2x. So I need to find the slope at x equals pi over 6, right? So at x equals pi over 6, the derivative would then equal minus 2 times sine of pi over 6 times sine of pi thirds, because it's 2 times pi over 6, plus cosine of pi over 6 times cosine of pi thirds, same thing, right? Twice pi over 6. Okay, then this is going to equal minus 2 times, this is 1/2 times 1/2 times square root of 3 over 2 plus square root of 3 over 2 times 1/2. And notice that all this should give me negative square root of 3 over 4. Okay, so then that is the slope at the point of tangency. So I have all the information I need to find the equation, because remember that the point slope form of the equation, just to recall, is y minus y1 is equal to m times x minus x1. So plugging into this, we have that it's y minus 1/4 is equal to minus square root of 3 over 4 times x minus pi over 6. And then if we expand and simplify that, we're going to get the equation y equals minus square root of 3/4 x plus 6 plus pi square root of 3 over 24. All right, so here we are with the quotient rule. And here's an important note. Just as the derivative of the product of two functions is not the product of their derivatives, the derivatives of a quotient of two functions is not the quotient of their derivatives. So what that means is that if you have an expression like 2x minus 1 times 3x squared plus 2, this, as we know, does not equal 2 times 6x. That would not be true. And same thing for a quotient. If you have, say, x over 2x squared, this would not equal 1 over 4x. We actually have to apply another rule, which is this one that we see here. So the rule is that you multiply the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. So here we have it in words. Derivative of quotient is equal to denominator times derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. Another way I like to think about it is as going low d high minus high d low over low squared. Now this is just a little memory trick. It's important to do it in the right order because of this guy here, right? If we do it in a different order, then the results would be wrong. Okay, so here we are in example 13.7, and it says that for each function find its derivative, 1 by the quotient rule, and 2 by another method. Okay, so we'll do them one by one. So let's start with A, and we're going to find the derivative of g of x. Okay, so remember that we do low, so low, d high, derivative of the numerator, that would just be 5 times 5, minus high, which is 5x minus 1, by d low, which is going to be 6x, so this time 6x, over low squared. So that's going to be 3x squared squared. So the next thing that you're expected to do is to expand and simplify this. Okay, so this is going to be 15x squared minus, and this is where you have to be careful with the signs. So this is going to be 30x squared minus 6x over 9x to the 4. And then we can simplify this more. Let's do it over here. This is going to be equal to 15x squared minus 30x squared plus 6x, all of this over 9x to the 4. And this is equal to negative 15x squared plus 6x over 9x to the 4. And we can simplify this more by factoring out, let's say, 3. So 3 and x as well. So 3x times negative 5x plus 2 over, notice that we can separate this as 3x times 3x to the 3. So now we can cancel this out. and we're left with this expression. Okay, so now I'm going to get rid of this and do it by another method. And that other method would be splitting this, right? So if I have that g of x is equal to 5x minus 1 over 3x squared, I can separate these terms into 5x over 3x squared minus 1 over 3x squared. Then I can rewrite this as 5 thirds x to the minus 1 minus 1/3 x to the negative 2. And then I can just use the power rule on these individual terms. So then, if I do the derivative, I'm going to get minus 5 thirds x to the minus 2 plus 2/3 x to the minus 3. Now we still don't have the same expression, so we have to work on this. Notice that this is equal to minus 5 over 3x squared plus 2 over 3x cubed. Okay, since I want to add these and I have 3x cubed here, I'm going to have to multiply this by x, therefore this by x as well, and then I'm going to get the same expression that I had before, which is minus 5x plus 2 over 3x cubed. Okay, so now let's work on b. So first let's use the quotient rule. Okay, so the derivative of h would then be, remember it's low d high, right? So low is 2x minus 3 times d high, the derivative of 1, which is a constant, will be 0, minus high d low, so 1 minus 1 times the derivative of the denominator, which is just 2. And this over low squared, so it's going to be 2x minus 3 squared. And then we can rewrite this simply as minus 2 over 2x minus 3 squared. All right, so now we're going to use another method. And obviously the easiest method is to rewrite h of x as 2x minus 3 to the negative 1 and apply the chain rule. So then applying the chain rule here, we would get that this is equal to minus 1, remember the derivative of the outside first, times 2x minus 3, not altering the inside, to the power of minus 2, times the derivative of the inside, right? And this is obviously going to equal minus 2 over 2x minus 3 squared, just like the previous. Okay, so here we are now on part C. And first we're going to do it by the quotient rule, right? So the derivative of f of x is going to be low, so 2x minus 5 times d high times 3 minus high, 3x minus 2 times d low times 2 over low squared. So this over 2x minus 5 squared. And this we can expand and then simplify. So this is going to equal 6x minus 15 minus, and I keep the parentheses here just to be careful with the signs. So 6x minus 4, all of this again over 2x minus 5 squared. And this is equal to, notice that this is going to be minus 6 and this is going to be plus 4. So we're going to get this to cancel out, and negative 11 over 2x minus 5 squared. All right. Now you're going to see how much easier this is compared to using another method, but I'm going to use the other method next. Okay, so we're going to use another method for part C. And to do that, we have to rewrite f of x as a multiplication. We can say that f of x is equal to 3x minus 2 times 2x minus 5 to the negative 1. Now notice that here we can use the product rule. So the derivative would be equal to the first factor, so that's 3x minus 2, times the derivative of the second factor. But we have to apply the chain rule for this one. So this is going to be minus 1 times 2x minus 5 to the minus 2 times the derivative of the inside, which is just 2. And this plus the second factor, which is 2x minus 5 to the negative 1, times the derivative of the first factor, which is just 3. Okay, so now we're going to expand this a little bit, organize it, and see what we can do. So this is equal to negative 2 times 3x minus 2 times 2x minus 5 to the power of minus 2 plus 3 times 2x minus 5 to the power of negative 1. And now what I'm going to do is that I'm going to factor this out because it's a common factor. 2x minus 5 to the negative 2. It has to be the lowest one. And this times negative 2 times 3x minus 2 times 3x minus 2 plus 3 times 2x minus 5. Notice that this is to the 1, because in order to get this, very well, so let's simplify this, and we're going to actually get that this equals 2x minus 5 to the power of negative 2 times, let's keep it in parentheses for now, let's say this is going to be minus 6x plus 4 plus 6x plus 6x minus 15. So notice that this will cancel out, and this is equal to negative 11. So we're left with the same expression again, which is negative 11 over 2x minus 5 squared. So we get very well. So here we are now in example 13.8, and it says given y equals 1 over x, find a formula for the nth derivative. So this is part of what's called higher derivatives. Now higher derivatives are just doing derivative after derivative after derivative. So you have a second derivative, third derivative, fourth derivative, etc., etc. In this problem, what they want us to do is to find a pattern. So if we can find a pattern and generalize it, we can find a formula for the nth derivative. So let's look for that pattern. First of all, notice that y equals 1 over x. We can write that as x to the minus 1. So the first derivative would then be minus 1 times x to the minus 2. And this is the same as minus 1 over x squared. All right, so now let's do the second derivative. So this is equal to minus 2 times minus 1 times x to the minus 3. So this will be 2 over x cubed. 2 over x cubed. All right, let's do the third derivative. So the third derivative, and notice that I'm purposefully keeping the numbers as coefficients to find the pattern. So the next one would be minus 3 times minus 2 times minus 1 times x to the minus 4, and this is equal to, or negative 6 over x to the 4. Okay, so let's do now the fourth derivative. So the fourth derivative would be then equal to minus 4 times minus 3 times minus 2 times minus 1 times x to the minus 5. And this is going to equal 24 over x to the 5. One more. I think one more should be enough. So the fifth derivative. The fifth derivative would be then minus 5 times minus 4 times minus 3 times minus 2 times minus 1 times x to the minus 6. And all that should equal negative 120 over x to the 6. So I think we found a pattern. So what we want is a rule for the nth derivative. So there's a couple things here to notice. The first thing is that we have alternating signs. Notice that the first derivative was negative, second derivative is positive, third derivative is negative, fourth derivative is positive, fifth derivative is negative. So that means that we have to take into account an alternating negative. So that is gotten by using negative 1 to the power of n, because depending on n, we will have a negative, right? So when n is odd, we get negative. And when it's even, we get positive. So notice that we get a succession of numbers that are multiplying in descending order, and that's just a factorial. So that's n factorial. So this would give us the numerator, and the denominator would simply be x to the power of n plus 1. So this would be a formula for the nth derivative of 1 over x.